Okay, sorry about that. I accidentally hit the wrong button. I meant to hit pause and I hit stop and it stopped the video. So let's continue on here. So substrate specificity of enzymes. So we just talked about how enzymes lower the activation energy and therefore make the enzymes or the reaction happen quicker. And so enzymes, let's talk about how they work and how they do that. How do they lower the activation energy? And so they are very specific. And so the reactant that an enzyme acts on is called the enzymes. We're going to write here substrate. And the enzyme binds to a substrate, forming what we call an enzyme substrate complex. So the active site is the region on the enzyme where the substrate binds. So here's a generic picture here. This is your enzyme right here. And this right here is your active site. So it has a specific shape, and that shape fits with a particular substrate. And so you can see this part here will fit, has the right shape to fit right into that shape of the enzyme. And remember that enzymes are really, let me get a different color here, a polypeptide chain of amino acids that has a particular shape here that allow the active site to have a particular shape. And so it's stabilized by the bonds between those R groups and so on and so forth. So let me give an example of this, a real simplistic example, using this above reaction with sucrose being broken down into glucose and fructose. So you have an enzyme. So here's your enzyme. I'm just going to draw a molecule like this. And this right here is its active site. So this right here, this is the active site. And this right here is the enzyme. And then we have, let's do this one here. This is, let's do here, sucrose. So this is sucrose. Sucrose is made from glucose. I'm going to put a G and a fructose, but they're bonded together, so it's a disaccharide. And so what happens is this, if we turn it over this way, can come over here and fit into the enzyme's active site. So when that happens, all right, this is what we see here. That's supposed to be the same thing. You guys know I'm not a great artist here. And so bonds in here, so this is glucose and fructose. So that's your sucrose molecule coming in. And so this is called this right here, when this happens, this is what we just wrote up there, the enzyme substrate complex. And then afterwards, look at what happens. The enzyme is not used up, so the enzyme is just like it was beforehand, and then it releases the two products that are no longer bound together. We have glucose and fructose, and so these guys are your products. All right, and so this right here was your substrate, sucrose. And so, long story short is that the enzyme has helped speed along the breakdown of sucrose into glucose and fructose. And we're going to see in just a minute that it does that by putting some stresses on the bonds that hold it together that makes it easier for those to break apart. And so therefore it doesn't have to absorb as much energy and therefore lowers the activation energy. So this picture here shows you what I just kind of drew simplistically. The same idea here, and in this case here, now it's a different reaction, and you have your two substrates, let's say A and B, all right, molecule A and molecule B, these are your substrates. They fit, here's your enzyme. Your enzyme has a specific shape, And so those substrates fit into the active site. And if you notice here, from here to here, the enzyme kind of changes shape a little bit. It kind of hugs around the molecule and the substrate. I'm going to show you a little picture here. So it's called the induced fit. So if this is your enzyme here, this is your active site right here, and this is your little substrate molecule. The substrate molecule fits into the active site, and then notice here it kind of like the enzyme hugs a little bit around that, changes shape and so on. And so that's called the induced fit. And so my analogy is it's giving the substrate a little hug. And what that does is help to put stress on bonds that helps to create or convert the substrates into product. So when it's doing that, it lowers the activation energy. So the active site can lower the activation energy and speed up a reaction. So let's talk about how they lower the activation energy here. So it can provide a template for orientation. So meaning that the molecules are lined up right to react. So they're not like, upside down or whatever, so that they're put together in such a way that the parts that are going to bond or whatever are together. It can stretch the substrates. Stretch the substrates toward their, what is called their transition point, meaning that it puts stresses on the bonds. All right. And when it stresses those bonds, less energy is needed to break those bonds and to cause them to reform, and so on. And then, lastly, it may provide a microenvironment more conducive for the reaction, for that type of reaction. So what does that mean? So in here, it may make like the R groups of the amino acid chain may create a little microenvironment that makes it more acidic just in here in the active site. And so therefore help speed up a particular type of reaction, or help like the H pluses to be transferred to the substrate if that's part of the reaction. And so you have this little microenvironment, and this is the enzyme because it's not clear there. Okay, so that's how it can lower the activation energy. And so then they are converted to products. So now we have our two molecules here that are different. So they're trying to show you they're different. Then here they have different shapes. And now we have our products. And so products C and D. And so and then the enzyme is not used up, and the enzyme can go find new substrates and convert them to product, and so on and so forth. So we would write this reaction, this generic reaction, A plus B, that's our reactants, gets converted to C plus D, and oftentimes the enzyme, the name of the enzyme is written on the arrow here, showing that the enzyme is not actually part of the reaction, but it is used to speed up the reaction. And so that's what we see here on the flip side, with sucrose being broken down into glucose and fructose, and sucrase doing that. All right, and so this is another example. So here we have a molecule like sucrose being broken down into two molecules. Here we have two molecules being converted into two different molecules. And so, to relate this to catabolic and anabolic pathways, these pictures just show you that enzymes can do both of those things. So here you have a molecule This is your enzyme substrate. Here's your active site, enzyme substrate complex, and it was being broken down into 2 different molecules. And so that is catabolism, or breaking the molecules down. And then anabolism, or anabolic pathways, are just the opposite. We have the 2 molecules that we start out with fitting with the active site. All right, and 1 molecule coming out. All right, so these guys come together, and showing you that these guys come together and come in here. It's hard to see that particular example there because it's not color coded. Let me show you up here like this. So here they come together, one fits and the other fits here. They're both in there, and then they become 1 molecule, and that would be an example of anabolism. Okay, so it doesn't always have to break down molecules. That's what I'm saying. You can build molecules and break down molecules with enzymes. So this just shows you the induced fit that we just talked about. So that when the substrate fits into the active site, gives that little hug, and so or a clasping handshake where it comes around it. All right, and so. All right, or a little hug. All right, and so then an enzyme's activity can be affected by several things. It can be affected by temperature. This is a review from the macromolecules when we talked about proteins, pH, and different chemicals like salts, salinity as well. And so this just shows you here, this is optimal temperature for 2 different enzymes. And so this is a typical human enzyme, all right, has the greatest rate of reaction at about the human body temperature. 98.6 degrees is 37 degrees Celsius. And so we have the optimum temperature. If we go one way or the other, it drops. And notice here that it drops faster as it gets hotter, because when it gets hot, the kinetic energy increases and the enzyme unravels and loses its shape. When it gets colder, the enzyme doesn't lose its shape when it gets colder. When it gets colder, it just slows down. So if you have an enzyme here and a substrate here, and the temperature goes down, the enzyme's still in the right shape, but they're just moving around so slow that the chances that that enzyme is ever going to meet that substrate to have a reaction really goes down. And so the reaction gets slower and slower and slower and slower the colder it gets. Now notice here, optimal temperature for enzymes of thermophilic bacteria, heat-tolerant bacteria. So these guys live in very hot conditions, and they're able to survive in hot conditions because their enzymes are not denatured in those hot conditions. Their optimal temperatures is 77 degrees Celsius, which our enzymes would be way denatured. Nothing would be going on. We'd be dead. But their enzymes, that's their optimal temperature. So again, getting much higher than that, it drops down pretty quick because they're denatured. Here, it goes slowly because they don't run into each other as much. And so the same thing goes with pH. And so we have pepsin and trypsin, 2 different enzymes. This is in the intestine where the pH is basic. Here's in the stomach where the pH is acidic. And so pepsin in the stomach has an acidic optimal pH, so it's high rate of reaction. And you get too far above or below that pH, and that rate of reaction goes down. Same thing for trypsin. It's in the intestine. It is basic, and so its optimal pH is basic, and you get too far either way, and the rate of reaction goes down. So every enzyme is specific to the substrate, and they're specific as far as the environment in which they thrive. All right, and so this is where I'm going to stop for this video.